is, okay, we have derived equations for the currents of the transistor. We know how the transistor behaves with various voltages and stuff like that. That's fine. But how are we going to use this transistor? Invariably, we are going to only use this transistor either to charge a capacitor or discharge a capacitor. This entire course is all about that. How fast you can charge the capacitor, how fast you can discharge a capacitor, right? This capacitance can be because of its own parasitic capacitance, like I will discuss today, or it can be because of a load capacitance, right? So I have a capacitance discharging. So if I have a logic inverter driving a load capacitance, right? This inverter is going to either charge this capacitor or discharge this capacitor, and the delay of the gate is determined by how fast this action can happen. Okay. So I also told you that delay is defined as the time it takes for the input to go to 50%, right? From there till the time the output reaches 50%. Okay. So if this is my VDD by 2 and this also is VDD by 2, then the delay of the gate is defined exactly as this delay. Okay, this is the delay. And we want to estimate this. Okay. So the simplified picture is, we have a capacitor CL and an NMOS is going to discharge it. We will see why an NMOS cannot charge the capacitor or a PMOS cannot discharge a capacitor. We will look at it later. Okay, but for now let's just look at this picture. The capacitor is charged, Vc of 0 minus equals VDD. So this inverter is going to now discharge the capacitor through an NMOS transistor. Okay. So this voltage V0 is going to fall from VDD to VDD by 2 because of the delay definition. That's why VDD by 2 is a very sacrosanct number. I am not worried about taking it all the way to 0. Okay. Now we have to make some assumptions to simplify our analysis, otherwise it becomes very difficult. So if for example, if the input is going to rise slowly like this, then that delay becomes a little hard to handle, right? If it becomes a ramp function, then I have to see when the device turns on, when it goes into linear, saturation, all that. It's very painful to do that. So we have to make some approximations to get a first order number, and then we'll incorporate this input slew also later on. So the assumption we are going to make is the input rises instantaneously to VDD. Okay, 0 to VDD instantaneous. Okay. So if at 0 plus the gate is at VDD, my V out is also at VDD, right? At 0 plus, just after I turn it on, in what region of operation will my transistor be in? Saturation region or velocity saturation, right? Because VGS is equal to VDD, obviously VDS has to be greater than VGS minus VT. You are removing some quantity from there. Therefore, the transistor is in saturation region. Okay. So the currents look like this, ID, okay, and this is V0. So, right, this is my point where it is VDD, this is VDD, and somewhere here is VDD by 2. I am assuming VDD is large enough such that it's to the right, VDD by 2 is to the right of VD sat. Okay, so that I don't have to deal with a change in region of operation. Okay, So this is an assumption. So what is the equation of the current IDS? Let's say it's velocity saturated. It is Kn prime W by L into Vd sat n into V. What is VGS? VDD, right? VDD minus VTN minus Vd sat n by 2 into 1 plus lambda V naught. Suppose this is a long channel device, then this would be in saturation, where this would just be Kn prime by 2 WL, VGS minus VT, VDD minus VT the whole square. Okay. So let me not worry about all that. I will just write this as I naught into 1 plus lambda V naught. Okay. Whether it is velocity saturated or not, or it is in saturation, I naught is independent of V naught. That's the only thing I am worried about. Okay. So now just look at the picture. The V naught is coming down. It's being, the capacitor is discharging, right? V naught is just the voltage across the capacitor, and the voltage is coming down. So if you look at the resistance, it now becomes a function of V naught. Okay. So last class somebody asked me, why don't you do a derivative out here? See, in analog it's okay to do a derivative because you fix your bias somewhere here, and then you will do some sort of a small signal analysis over that bias point. So in some sense we have linearized this whole thing here. So when you do a Taylor series there, you got to take a derivative and then you expand it in terms of the input variables. So therefore you take derivatives there. But here I am actually discharging it from VDD to VDD by 2. It's such a large range, right? So I cannot do that small signal analysis of taking a derivative here. I have to find some other way of finding the resistance, average resistance now, which is a function of V naught, right? So R of V naught is simply what? V naught by I naught into 1 plus lambda V naught. Now I have a function f of x that is going from a to b. I want to find what's the average value. What do? You just integrate and divide by the x2 minus x1, right? That's all I'm doing here. So I'm saying that R equivalent is defined as V final minus V initial into V initial to V final of R of V naught dV naught. That's what I'm defining as the average resistance. Okay. So this I will now write as minus VDD by 2, because VF is VDD by 2, VI is VDD, and so I'm going to write this as VDD to VDD by 2 into V naught by I naught, right? That 1 by 1 plus lambda V naught I am going to write as a Taylor series because lambda is very small. Okay. I can expand this approximately as 1 minus lambda V naught. Okay. Maybe I should put an approximate here, dV naught. Of course, now I naught is a constant, so I will just write into 2 by VDD into V naught into 1 minus lambda V naught dV naught, right? So what did we get the answer here? You solve the integration and you just get what? 3 by 4 VDD by I naught minus 7 by 12 lambda into VDD squared by I naught, right? This is what we got. Fine. So if it is going to have channel length modulation, then this is the only way you can do it, because there is a variation of resistance all through because of that 1 plus lambda V naught, right. So now the interesting thing is, if it's a long channel device, then lambda is equal to 0, okay. So implies R equivalent is 3 by 4 VDD by I naught if lambda equal to 0. Okay, so the point I was trying to make last time is, okay, we found an equivalent R, right. Why are we finding equivalent R? Because I can now treat this as an RC discharge and I can evaluate delays in terms of the time constant of that RC network, okay. But if lambda equal to 0, then this is just like a constant current source discharging my capacitor. Why is it a constant current source? Because there is no dependence on V naught. Now if lambda equal to 0, the current basically just becomes a IDS versus V naught. This simply becomes a flat line, and this is my region of operation from VDD to VDD by 2. Okay, and of course now I don't even have to worry about VD sat, because this will always be in this thing. No, you have to still worry about it. You have to make sure that the VT is above some number, below some number, for it to be in saturation region all through. Okay, so assume VDD is high enough, there is no problem. So this is now like a constant current source discharging the capacitor. Okay, so we did the same calculation in method 2. So it's a constant current source discharging my capacitor. Method 1 is, you had a thing like this, R equivalent into and CL. Now what is the time it is going to take to, and what is this? This current is I naught, by the way. If lambda equal to 0, this current is just I naught. What's the time it's going to take to discharge from VDD to VDD by 2? If it's a constant current source discharge, C delta V by I, right. So the time is C delta V by I naught, CL, right. CL into VDD by 2 divided by I naught. Here the R equivalent was 3 by 4 VDD by I naught, which implies that the time constant of this RC network, right, let me call it tau prime, is R equivalent into C. Now the delay of this thing to come from VDD to VDD by 2 is 0.693 times the time constant. So this is 0.693 into 3 by 4 VDD by I naught, right. So this is approximately, again we'll get 0.51 or 52 or something like that. I naught into CL. Now these two answers indeed do match, right. Now obviously if lambda is 0, then the constant current source model is the right model, because the transistor is a current source. Okay, so if you look at the model that we are using for delay, okay, this guy is, if you look at this V naught of t, it will start from VDD and then go linearly, right. What is this? C dV by dt equal to I, so I naught by C into t. Whereas this guy, if you see, V naught of t is VDD e power minus t by tau prime. So the two models actually follow different equations with respect to time, but this one is more accurate. Okay, so if you look at V naught of t versus t, you have a straight line like this for method 2. the method 1 is going to look like this. Asymptotically it will go down to this thing. So this is my delay tau and this is VDD by 2. So the two models give the same answer at that particular instant of time. Any other instant the two models are different, right? The delays are the same. Question, why do you even want to do it through the resistance method? One is, of course, if there is channel length modulation, then this current source thing fails. I have to now, if you can of course solve this from first principles by saying that I equal to minus C dV by dt and use the equation of the make I dependent on V and solve the differential equation, then it's fine. Otherwise, I need to do it through this resistance method, which is a reasonable approximation, because all I am worried about is the delay at when it comes to VDD. This is the only point of interest in this model for me. So if you ask me which is better, it really doesn't matter, right? And I also pointed out that beyond this, both the models are actually not valid, because when it drops below VDD by 2 and eventually goes below VD sat, the transistors goes into a linear region of operation, right? And there the equation itself changes. So when I do that resistance calculation, it will go into a different region of operation altogether. So that is not even worth sort of going through all the way down to 0 with that equation, because it's not of interest to us, okay? So beyond this, invalid model. The reason I am pointing this out is you will see that we use certain models in this course which are valid only in certain regions of operation. Outside that region of operation, if you ask me what the value of the model is, I would say I don't care, because the model is not even meant to handle that region of operation. That's the point I am trying to drive home here, okay? Any questions? So the other thing is, of course, later when I start putting transistors in series or in parallel, then it's very easy for me to reduce that network using series parallel resistance combinations if I know R equivalent. Current source model, I cannot do that, okay? Any questions here? Okay, so let's look at this equation a little more closely. R equivalent is 3 by 4, I leave out this lambda parameter, I naught, okay. If it is velocity saturated, then I naught is equal to Kn prime W by L Vd sat n into Vdd minus Vtn minus Vd sat n by 2, okay. If it is a long channel device and it enters saturation region, then it is just Kn prime W by L into Vdd minus Vt whole squared and half, right? This is saturation, velocity saturation, it doesn't matter. So this is a long device, this is a short channel device. Okay. So look at this equation of R equivalent now, right? Clearly it is going to be inversely proportional to W, 1 over W, because the I naught is sitting below, right? So therefore, if I double the width of a transistor, then the resistance of the transistor drops by a factor of 2, right? Or the resistance becomes 50% of what it was earlier. So this is one key technique that we will use. If you want to reduce your resistance, then you upsize the transistor, and that is what this equation is also telling us, right? Now what happens if VDD is very large? Suppose VDD is very large such that VDD minus VTN minus VD sat n by 2, right? Or VDD is very large compared to VT, then what will happen? Yeah? If it's velocity saturated and VDD is very large, what happens to the R equivalent as a function of VDD? Yeah? But there is also an inverse dependence on 1 by VDD minus VTN minus VD sat n, no? So, if VDD is large, right? What does large mean? That is VDD minus VTN minus VD sat n by 2 is nearly VDD, right? This is just a first order thing to show you that R equivalent then is not a function of VDD. So if I have a 180 nanometer device and I operate it from 1.8 volt down to 1.5 volt, then the R equivalent will not change much there. Okay. On the other hand, if your VDD is very small, then of course these things cannot be neglected, and that has a more complicated relationship with VDD. In this course, we are going to deal only with higher VDDs. We are not going to bring down the VDD close to subthreshold or even low voltage operations. Okay.